We are going to take a look at parts C through F of problem 1 of for 2022. I have a separate video for parts A and B, but you can watch this without having watched the previous one. Really, the key thing to know about this problem is that we have a table of h of x and h prime of x where all of these functions are defined and continuous at every point. Again, whenever you're given a table of values, you don't have much information about what's happening in between the table entries, but they are giving us an information in this problem by letting us assume that between the consecutive values of x in the table, h of x is either always increasing or always decreasing. Like, for example, between -4 and -2, we see that h of x has gone down. It went down from -0.5 to even more negative, -2. So we know h of x was actually decreasing here in between the table entries because they said we can assume this. But having pointed that out, let's dive into the question. So part C, we wish to find integral from -4 to -2 of 2 times h prime of x plus x dx. And here for part C, we want to find the exact numerical value or write not enough information if there's not enough information. And here we see that we're adding functions and we're multiplying by just a constant. And something to remember about the integration is that with respect to addition, subtraction, or multiplying by just a number like 2 or some constant, integration behaves exactly like you want. So for example, we can use plus to break down this integral to integral from -4 to -2 of 2 times h prime of x dx plus integral with the same bounds of x dx. And to this number, we can actually move that outside the integral. So we can actually just have 2 outside here. So note that 2 here goes with this integral, but not with this integral, of course. And that's because 2 was only multiplied to h prime here. I guess something important to be pointed out is that if I'm multiplying two functions, like f of x times g of x dx, then the integral does not behave so well in general. So in general, when I'm multiplying two functions like this, you cannot say that integral of a product is actually the product of the separate integrals. It doesn't work like that in general. And intuition for this, I guess, is that if you know fundamental theorem of calculus, which you hopefully know for this problem, then there is an intimate connection between the definite integration, which are finding area under a curve, signed area under a curve, and anti-differentiation. So anti-differentiation is of course connected with differentiation. So if you remember how the derivative works, when I'm adding things or when I'm multiplying by 2, taking differentiation, taking derivative behaves very well. But when I'm taking product, differentiation behaved in a pretty bad way. You had to use the product rule to actually differentiate something like this. And it's very similar for integration. The integration behaves well under multiplying by 2 and addition, but it doesn't behave well under multiplication. Anyway, so that's a bit of a digression, but we have this expression. How can we find it? Well, for this part, we can use fundamental theorem of calculus here. So for example, we can try computing this integral. How do you compute a definite integral exactly? Well, you can compute it exactly either by finding the signed area under a curve. So here, in fact, graphing x is pretty easy and you can easily find the signed area here, and that's one way if you're provided a graph of a function. Maybe that's the easiest way. Or we can anti-differentiate it if you know how to anti-differentiate this function, and then look at the change in the antiderivative from -4 to -2. Let's start by finding the antiderivative of x. What do we differentiate to get x? Well, we get x squared over 2. So again, when we differentiate x squared over 2, you should be able to easily check that we get x. I guess a common confusion is some people, rather than writing down x squared over 2, might be writing down 1, but you're not differentiating x. You're trying to find the function that we differentiate to get x. So you want to look at x squared over 2, and by fundamental theorem of calculus, you look at the change of this function from -4 to -2. All this is saying here, we look at the final value of the function at -2, which is -2 squared over 2, and we look at the initial value of the function at -4 minus -4 squared over 2, and we look at the change in x squared over 2, and this is 4 over 2, which is 2, minus 16 over 2, which is 8, so we get -6. So you know this integral is -6. I'm just using fundamental theorem of calculus here. I guess something to be pointed out is when you're doing indefinite integration, when I'm just finding the antiderivative of x, then you technically should write x squared plus over 2 plus c for some constant of integration. But when you're using fundamental theorem of calculus, you don't need to do this, because if I had plus c here, well, then you should realize that this plus c, because this is actually one quantity, we would have gotten this thing plus c parenthesis minus this thing plus c parenthesis. If I had plus c and I carried it along, and this plus c and this plus c cancel out because you have a minus sign here, which distributes. So plus c cancels out anyway, so we don't actually need to keep plus c around when you're doing definite integration. Anyway, so we got minus 6 here. What about the first integral? Well, again, we use the fundamental theorem of calculus. This is 2 times the quantity. Make sure you put the parenthesis here, because you're multiplying 2 to the entire integral, which is one quantity. And what goes inside the parenthesis? Well, you're going to have h at negative 2 minus h at negative 4, because the antiderivative of h prime of x is h of x. This is what you differentiate to get h prime, and we look at the change of it from negative 4 to negative 2, which is exactly this. And this hopefully is easy enough to find. We have that this is 2 times h at negative 2, which is negative 2, minus h at negative 4, which is minus 0.5. So negative 2 minus negative 0.5, that's negative 1.5. So you get negative 3 for this expression. So the entire thing is negative 3 plus negative 6, or negative 9. Before we move on, let me just mention maybe 1 or 2 variations. So rather than plus x, what if you had plus x cubed? Well, in that case, you wanna, rather than having x squared over 2 here, you'd have to figure out what do we differentiate to get x cubed, and that would be something like x to the 4th over 4, right? Because when I differentiate this, I get x cubed. What about if I had plus cosine x? Well, now the question is, what do I differentiate to get cosine x? And in that case, you would have had sine of x inside the brackets here, because when I differentiate sine, I get cosine. If I had plus sine of x, what's the deal? Well, what do I differentiate to get sine? Well, you have to differentiate negative of cosine, because when I differentiate cosine, I get negative sine, so you need another minus sign to compensate. And what if I had plus, say, like secant squared of x? Well, then you want something like tangent of x, because when I differentiate tangent of x, you know you get secant squared of x. So these are some other variations that you might see. So rather than plus x, you might get plus any of these pretty simple ones that you know how to find the antiderivative of, and you might have to work with them instead. I guess another possibility worth mentioning is if it's plus 1 over x, then of course the antiderivative would be natural log of x. And the final variation I mentioned, what if instead of h of x here, I had h double prime of x in the problem statement? Well, then you'd be anti-differentiating h double prime of x here. What do I differentiate to get h double prime of x? Well, that's h prime of x. So rather than doing h of negative 2 minus h of negative 4, in that case, you would have had h prime and negative 2 minus h prime and negative 4. So again, if I change the problem a little bit, then you should be able to adjust accordingly. Alright, going to part D, we want to find an equation for the tangent line to the graph of h of x at x equals to 6. So remember, to find the equation of a tangent line, we need two information. We need the slope and we need the point. So point is usually a bit easier to get. So we know the point here is going to have the x coordinate of 6. They tell you this. And the y coordinate should be h of 6. So whatever this y coordinate is, we're looking at the graph of a function, so it should be h of 6, which we know is 3 here from the table. So we know the point is 6, 3. What about the slope? Well, the slope of a tangent line is exactly the derivative of the function at this point. So we want to look at h prime as 6. And what's h prime as 6 here? Well, h prime as 6 is negative 2. So we know the slope should be negative 2. So we're looking for a line, equational line, that goes through this point with this slope. That's easy enough to manage. So we know we should have y equals to negative 2 times something, because that's the slope. And let's make sure it goes through 6, 3. And one easiest way of doing that is to write the parenthesis x minus 6 plus 3. Because now when I plug in x equals to 6, this thing vanishes. So we just get the output of 3. So this is exactly the line we want.